Okay, so next class is exam 1. And the topics are everything up through particle kinematics number 10. So that means no circular and spherical motion. And no relative motion. Okay, so the new material we're dealing with right now is not on the exam. Before I get back into that, anybody have any homework questions? Okay, do you have it with you? I didn't have a printout next to me. Oh, the swimmer. Okay. Okay, so this is not test-related stuff, but so the person's capable of swimming 4.5 miles per hour. So that's that has to do with the speed that the person can create between themselves and the water that they're in. Okay, if you're in a swimming pool that's in a train, you know, and the train's going 100 miles an hour and you can swim 4.5 miles an hour, then you're moving 104.5 miles an hour. It doesn't, the overall speed compared to the earth doesn't matter. What matters is the speed compared to the water. Yep.
I actually wondered about that 4.5, and I thought, okay, well, if you convert it to the water is a coordinate axis, or whether the water is the observer.
Yeah.
Because otherwise, it doesn't make. I mean,
right.
4.5 is relative to the ground, unless you think, well, the water is the observer, and not the plane.
Yes, exactly.
So that's kind of how.
So right. So you have to think of one of those coordinate systems as moving with the water. Okay. So let's see. And so the person's, here's the river. And the width of the river is 0.15 miles. And the river current is 8 miles per hour. And the person is going to be going perpendicular to that. So the person's going to be trying to swim straight across. So we can think of this as we're trying to come up with the velocity vector of the swimmer relative to the ground. And that's equal to the velocity of the swimmer relative to the water plus the velocity vector of the water relative to the ground. Swimmer relative to the water, the swimmer is going to be just going in the, so if you have a coordinate system that's floating with the water, okay, so this coordinate system, this is the one we're calling W, okay, and the swimmer. That's a sloth. Okay, so the swimmer, if you had a video camera on a buoy that's floating, on a floating thing going along with the water, that would just see the swimmer going straight across. But something on the shore is going to see the swimmer moving with the water too. So the velocity of the swimmer relative to the water is 0, 4.5. The velocity of the water relative to the ground, that's going in the positive x direction the way I have it drawn. So that's 8, 0. And so an observer, a camera that's fixed on the shore would see the swimmer moving with a velocity vector of 8, 4.5. So how far down the river will the person be when they get to the other side? That's a really tall person. That person's like well over half a mile tall. Okay, well, to get to the other side, we're treating this as a constant velocity. There's no acceleration. So you can think of it as distance equals rate times time, or to be a little more careful with it, you could use the constant acceleration equations from physics. Or if you wanted to be really, really careful about it, you could start with the fact that acceleration is 0 and as a function of time and integrate up all the way to position. But if we use this equation that says, so first I'll go P y is equal to P0y plus V0y t plus 1/2 AY t squared. Okay. Anybody recognize that form from Physics 1? You might also see it like this. Okay, well, and acceleration is 0, so that goes away. All right, what if you didn't remember that? What if you never took Physics 1? So let's say that acceleration vector is 0. At time 0, when time is equal to 0. Then you could integrate that to come up with the fact that the velocity as a function of time is equal to some constant c, cx, cy. I'll just call that, so those are constants. And then you can integrate that, and position as a function of time is equal to Vxt plus c, I don't know, 2x Vyt plus c 2y. If we think of the shore as 0, then these go away. So now we have this position function that's just equal to Vxt, Vyt, which all this was just a fancy way of figuring out the distance equals rate times time. So the y position at time t, if we're trying to figure out how long it takes to get across, Well, the final position is 0.15. This is the y component of this equation. So 0.15 is equal to the y velocity, 4.5 t. And so t is equal to 0.03 hours, I think. And now you can plug that into the x equation. So px is equal to 8 times 0.03, and that is 0.24 miles. Is that right? 0.03. Yeah.
Why did the constants go to 0?
So those are just saying, so here we basically just said our origin, we said at time equals 0, call the position 0, 0. So we're just trying to figure out how far, we're just talking about going a distance of 0.15 miles. So there's no reason to call those anything else when time is equal to 0.
Which velocities and accelerations are we attaching these to? Is this the swimmer relative to the ground?
The Vx and Vy? Yeah, those are from the relative motion equation. So this is what we know the velocity is during that whole motion. We figured that out from relative motion. And then after that, we have to use the distance equals rate times time stuff to go from that velocity to how far you go over a given time.
So the coordinate system used is swimmer relative to the ground.
Yeah, once we do this, once we get to this step, from then on, everything is relative to the ground. Yep. Mm-hmm. Well, yeah, so we have, so what we have is, we have a position function, right? And these two things are constants. So let me write those in. So this position function says, position is equal to 4.5 t. Nope, I did it backwards. This should be 8 t, and then 4.5 t. Okay, so now we have this position function. Now, well, we know when we get to the other side, these have to be the same. I'm going to use the y equation to calculate when y has changed by 0.15 miles. That's when you get to the other side. Calculate t and then plug it in for x. Any other questions on that one? Any other homework questions? Yeah. Anybody have that those problems? Number 6. Okay, so d dt of the quantity 2xt squared is equal to 50. Where at time 1, x is equal to 5. Okay, well, the first thing you might think is take the derivative and see what you can do. So the first thing you try is if you take that derivative, you get 2x dot t squared plus 4xt is equal to 50. And once you get here, you can't use separation of variables. This one doesn't work with separation of variables. But what you can do is instead just temporarily define this new variable. Let's say z is equal to this thing, 2xt squared. You know, z is a function of time. So whatever x is, it's a function of time. And then we're multiplying it by 2t squared. So we have this new thing. That's totally fine. And now our differential equation says time derivative of z is equal to 50. We also have to change the boundary conditions. This is a z with the cross through it. It's a 2 on the right side. Okay, so the boundary conditions now, when time is equal to 1, x is equal to 5. So put in 1 for t, 5 for x, and that gives you a new value. So when at t equal 1, z is equal to 1 squared times 5 times 2, so z is equal to 10. And now it's a pretty easy problem to solve by separation of variables. So you get dz integral is equal to integral of 50 dt. So z is equal to 50t plus c. And I suppose there's a couple ways you could do it. You could change the boundary conditions like this and solve it for z and then go back and solve for x. Or you could leave the boundary conditions alone. We have our function for z, now solve for x. Two ways to do it, but you'll get the same thing. So 10, you know, the boundary condition here says ten is equal to 50 plus c. So c is equal to negative 40. So z is a function of t is equal to 50t minus 40. Well, we don't want z. We made up z ourselves, so nobody asked us for that. We want x. So now we have to substitute back in 2xt squared is equal to this thing that z is equal to. So x is equal to 25 t to the minus 1 minus 20 times t to the minus 2. Any questions about that one? Yeah. Yes. No, that's okay. So yes, you could also do this. Maybe this is an easier way to think about it. So, here's what we have. d dt of the quantity 2xt squared is equal to 50 where x of 1 is equal to 5. Okay, so let's do separation of variables right now. And the thing on the left is d2xt squared. And the thing on the right is 50 dt. And now we can integrate both sides. If you integrate, you know, this infinitesimal increment of 2xt squared, you get 2xt squared. And that's equal to 50t plus c. And now the boundary condition, so we have 10 is equal to 50 plus c. So c is equal to negative 40, and it all works out the same, yeah. Why does what? So, you know, like when you integrate, so what we're doing here is when you integrate, you have this infinitesimal thing, and you're just adding up an infinite number of them. It's just a sum, okay? Like normally we do it for an infinitesimal piece of x or an infinitesimal piece of y. This time we're doing it for an infinitesimal piece of 2xt squared, okay? And if you add up all the infinitesimal pieces of 2xt squared, it gives you 2xt squared. Okay. So that's really exactly what we did before. You just skipped the one step of calling this something new, but it's the exact same thought process. Any other questions on that one? By the way, it doesn't come up so much like in this form, but the idea of finding a total derivative in your differential equation is a really useful thing in ODEs. Like, for example, what if I'd given this problem as where x of 1 is equal to 5. Okay, that's a crazy looking differential equation. You can't do it by separation of variables. But if you recognize, and who would recognize this, you know, like it'd be very unlikely that you'd be thinking in a way that, so it's not like this is an easy thing to spot. But if you happen to look at this and notice like, wait a second, that's a total derivative, I'm going to just write it as a derivative of something. Then you can solve it using the approach you know, you just have to notice that that left side, you know, more easily said than done, but you just have to notice that thing on the left side is this. And then it's relatively easy to solve. That's the idea of, I forget what the technique is called, multiplication factors or something, integrating factors. Integrating factors in ordinary differential equations is based on this idea. You're turning the problem into something with a total derivative, and that lets you simplify. Okay, we've already talked about this problem too much. Any other questions? Differential equations are cool. Like every law of science just about is a differential equation. And if you're good at solving differential equations, you'll always be in demand in, I don't know about professionally, but at least in groups in school and stuff. Everyone will want to be your friend. Probably not professionally, because then you just use a software package to solve it.
I have questions about 15 and 16.
Okay. Yeah, I think that's fine. 15. Oh, yeah. Does anyone have any more questions relevant to the exam? Yep. Mm-hmm. Yeah. Oh, well, I mean, you can, I do try to remember to do that because it makes it easier for me to grade, but if I don't give it, then you're welcome to use any orientation you want. Yeah, right. And even if you don't explicitly define it, I can tell by, you know. But yeah, I try to make it so everyone uses the same ones because otherwise it's such a nightmare to grade, you know. In vectors, sure. Do you have those? Vector problems? That's it. Okay, so number 16. Okay, so that's the one with this funny shape thing, right? And there's a cable that connects to the wall, and this angle is 45 degrees. And the center of mass is here. And let's call these points A, B, C for center of mass. And the cable length is 0.5 meters. The point A is 0.05, negative 0.2. The point B is 0.6, 0.4. And we want to calculate first if the cable tension is T, what's the force applied to the body by the cable? And then second, what's the vector? It says from the pin to the point where the cable contacts the wall. So we want the vector 2D from A. Okay, well, the force vector that's applied to the body by the cable is parallel to the cable away from the body. And so that, we can just write that as, P times the unit vector in that direction. And a unit vector in that direction is just cosine sine of 45. So that force vector is, so T cosine of 45, T sine of 45. So 0.7071 T, 0.7071 T. And then second, if we want a vector that starts at A and goes to D, we can think of that as the sum of two vectors. So we're trying to go from here to here. This is what we want. You could just come up with the coordinates of that point D and subtract, or you could think of this as the sum of a vector from here to here and a vector from here to here. The sum of those two green vectors is that red vector. Well, let's figure out the coordinates of D. Is that, yeah, D. So D is the coordinates of that point B plus the vector from B to D. So 0.6.4 the length of the cable times the unit vector in its direction. And so the coordinates of D are 0.9535 and 0.7535. And so the red vector, the vector we want, is D minus A. So So that's 0.9535, 0.7535, minus 0.05, negative 0.2. And so that's 0.9035, 0.9535. Any questions about that one? And then 19, that one's a little different. Let me do that one too. So this one, you have a beam that's connected to a pin joint at the wall on the right end. And on the left end, the pin slides in a slot. We're given that this angle is 45 degrees. And then we're given that the slot makes an angle with the vertical of 20 degrees. And we want to calculate a vector with a magnitude r perpendicular to the slot. And second, a vector from the wall pin to the slot pin. There are two, so for part A, there are two vectors that are perpendicular to that slot. One going this way and one going this way, and either one of those is fine. So I'm going to do it like this. Here's the coordinate system. And I'm going to draw the vector that we're given an angle for. All these vectors have to have their tails at the origin. So we're given that this vector makes an angle of 20 degrees with the negative y-axis. Okay. And now the vector that we're looking for makes an angle of 90 degrees with that one. Okay, so starting at the positive x-axis, what angle do we have to use to get to this one? Yeah, 290 or negative 70. And then from there, now we're facing that direction, so 90 degrees counterclockwise, so add another 90 to that. And you get theta is equal to 380, which is 20. But if you put in 380, it would work fine. Yeah, if you can recognize it. I mean, I suppose for this problem, yeah, if you can recognize it consistently, that's fine with me. But this is an approach that can be helpful when things get more complicated, because you can have things where like everything's given as an angle compared to some other angle. And this idea of like going from one to the other until you get to the thing you want is a useful thing to be comfortable with. Okay, so the vector is r cosine of 20, r sine of 20. Do the power series in your head, and you get 0.940 r, 0.342 r. What? Oh, okay. That was the one. Right. So the vector from the, I'll just mention, from the pin slot, no, from the wall pin to the slot pin, you're just trying to find a vector like this. Well, I'm going to do that the same way that I did this, actually. I'm going to do it, even if you don't want to see it. Okay, so let's use the angle that I happen to give here and figure out the angle for that vector. So the angle that we're given says from the positive x-axis to a vector like this is 45 degrees. So the theta for this is 45 degrees. The vector we want is the opposite of that. So you can do SAT math and figure out that this angle is 45 degrees, or you can figure out that that's 180 from this one. But this theta is 45 plus 180, so 225. The length is 4 of the vector we want, so we have 4 times cosine and sine of 225. Which is negative 3.464, I think, negative 3.464. Yep. No, that's perfectly fine. Yeah. So anytime you can see that stuff easily, feel free to use it. But this is a way that just always works. Like if you get sort of methodical about using this, the thing I like about it is it's programmable. You know, you can come up with algorithms that use this idea, and it'll come out right. But when I do stuff in my head, I do what you're doing. You know, like I picture the triangle and then do the signs later. Any other homework questions? Oh, time's over. Okay, see you Monday. Have a good weekend. Thank you.